Alright, this is Chapter 5, Section 2 notes. In this section we're dealing with log functions, or logarithmic functions, and properties of logarithms. You will definitely hear me refer to these things as just plain old logs a lot in this section, or in this chapter even. Alright, so the way log functions work is we write them as y equals, or sometimes, f of x equals log base b of x. Okay, that's the way we pronounce that. Log base b of x. Okay, and this kind of looks like an exponent, like b to the x power, but it's not. Okay, b is the base, right, and x is the input of the log function. So we don't always write it, but it's kind of like there's a parentheses right here. Okay, but again, it's not always written just because of the fact that if it's a single input, then it's just understood that it's a parentheses in there. Alright, a log function is another way to write an exponential function, meaning that this x equals b to the y is the same as y equals log base b to the x. Alright, they're one and the same. Alright, being equal to y, what this is saying is the same as b to the y power is equal to x. Okay, and the way this goes is you start with the base, you go across to pick up the y, and then you come back over and it equals the x. Okay, b to the y equals x. Now look over here in the exponential. This is what we call the log form, and then this over here is called the exponential form. Okay, so you'll hear me refer to these two things all the time. The log form of the equation, the exponential form of the equation, because they both literally mean the same thing. But look over here, the exponential form, y is the power on b. Okay, well, what is y equal to? Y is equal to the log base b of x. So what does that mean? Thus, a logarithm is an exponent. Alright, this confuses a lot of people. A lot of people don't like working with logs, but if you just understand these things are exponents, your life will be a whole lot easier. Okay, understand this conversion between the two, and understand the log is an exponent. It makes this section in this chapter much easier. Alright, so let's convert from exponential to log form. Alright, so for a, 3 squared equals 9. We want the equivalent log form of this. So the equivalent log form would be the log, alright, go back up to this previous slide if you need to. Alright, 3 squared equals 9. There's the 3. It equals 9. There's the 9. There's the 2. Alright, so it's the log of the base. The base is 3. Of this, what's on the other side of the equals the exponent. Remember, the log is the exponent. Alright, 4 to the negative 1 equals 1/4. That means that the log of the base, again the base is 4, it's what's being raised to the power, of what we get equals the exponent. Alright, the log is the exponent. Okay, remember, log, all of this is the log, is, there's the equal sign, the exponent. Alright, and then there was the exponent. Okay, so when you're making this transformation from one to the other, just always remember this thing over here that's on the other side of the equal sign, opposite the log, is what the original exponent was. Alright, C, 5 to the first equals 5. That's the log base 5. Alright, equals of these other two numbers, what is it? The log is the exponent, so the exponent's on the other side of the equals. So that means this other 5 goes there. Okay, this is a property we're going to pick up in just a little bit. This works for any time both of these are the same numbers, we'll always get 1 here. Alright, and then D, x to the 3, x equals 3 to the y. So this is the log of the base. The base is 3. So log base 3 of x equals the exponent is y. Okay. Alright, so there's the equivalent log forms of these things. Alright, converting from log to exponent form. From log to exponent. So for A, we have log base 2 of 16 equals 4. Remember, for these, when you have the log form, you go across the equal sign. So 2 to the 4th power equals, and then come back, equals 16. For B, 10 to the negative 4 equals 0.0001. And then C, 6 to the 0, come back across, equals 1. Alright, so that's how we go from one to the other. But remember, the log is the exponent. So that means that this is going to be the exponent. Log is the exponent. So negative 4 is the exponent. Log is the exponent. So 0 is the exponent. Alright, if you wanted to graph a log function, y equals log base b to the x, if you wanted to graph one of those, this is what you're going to see. It's a little bit almost like the square root function, in that it grows very slowly, but it keeps growing forever and ever and ever. The only thing that's different about this and the square root function is, first of all, it's x-intercept. Alright, this one has an intercept of 1, 0, and the fact that it keeps going down forever and ever and ever. So its range is all real numbers. Okay, the other thing that it kind of has in common with square root functions is its domain cannot have negative numbers. So we never have anything to the left side in a log function. Okay, now the slight difference is that, if you recall, the domain of the square root function was x greater than or equal to 0, and this cannot be equal to 0. We can't have 0 go into the log function either. Okay, now why is that? Why is it that we can't get negatives or 0 out of here? Well, remember, it's if the log base b, if we put 0 in there and we got x out of there, what does that mean? It meant b to the x equals 0. Right, and what is b? B is any number greater than 1. Right, or b is any number between 0 and 1. So b is positive. So we're positive, we raise it to a power, and we get 0. So there's no positive number. So there's no way a positive to a power equals 0 or negative. Alright, the only thing you can get if you start off with a positive to a any power is a positive. Okay, so that's why we can't have any negatives go into this thing. Alright, now then again, if the base is between 0 and 1, then it flips over the x-axis, and this thing is decreasing the whole time. Right? So if this is the case, if our base on the logarithm is above 1, then we increase the whole time. But if the base on the log is between 0 and 1, a proper fraction, or a decimal lower than 1, then we decrease the whole time. Alright, vertical asymptote, the y-axis, the line x equals 0, this is our vertical asymptote, meaning the graph will hug it and it'll get closer and closer to it, never touching it, never crossing it. Alright, and just like before, same transformation rules as other functions, meaning all the stuff that we've studied in the previous chapters. Here's your base function, y equals the log of x, y equals the log of x plus 3, so it's inside of parentheses, so that means it shifts left 3 units. And if you look, that's exactly what happened here. Here was the original function, had that asymptote at the y-axis. This one's been shifted left 3 units, so now that asymptote's at the line x equals negative 3. Okay, this crossed the x-axis at 1, right? This one crosses the x-axis at negative 2, so everything's been shifted left 3 units. Alright, this one, x minus 2 in parentheses, so that's right 2 units. And then plus 4 would be up 4 units. Right, and so all the transformations that we talked about before take place with logs 2. No difference. Right, those transformations are actually for all functions, not just the square roots and the x squared and stuff that we studied last chapter. It works for everything, so it's going to work for logs too. Right, and again, notice at any point on this graph, right, that's 1, 0, has been shifted right 2, 1, 2, and then up 4, and then we hit a point on this graph. Okay, so every point's like that on this graph. Alright, so a natural log. Natural log, we use ln to denote the natural log. The natural log is log base e. Okay, but instead of writing log base e, we write ln x. Okay, because it's so commonly used, it's got its own name. So here's a question that has it in it. Projections from 2010 to 2015 or 2050 indicate the percent of U.S. adults with diabetes can be modeled by this function, right? And then there's the ln on it, where x is a number of years after 2000. Okay, so this wants to know, is the function increasing or decreasing? What does that mean in the context? What does the model predict the U.S. adults with diabetes will be in 2022, and then use the graph to estimate that. So to answer the first question, let's graph it. Alright, then the negative 12.975 plus 11.851. Next thing I need to put is ln of x. So that's right here, the ln button. So I press ln, type in x. Now I'm going to start off in the Zoom 6, the Zoom standard screen. Alright, notice that it starts going up and to the right. Okay, but notice too that this says from 2010 to 2050. Okay, x is a number of years after 2000. So let's go from 0. We'll start in 2000, even though it starts in 2010. Let's go from 0 all the way up to 50, and then we'll adjust our height as needed. So that means we're going to take our window and start at 0, go all the way up to 50. Alright, and then if we graph that, alright, notice that this goes way up out of the screen very fast. So let's change our window here to be for the y-max, and then see what we look like. Alright, so there's the graph when I have this window. Okay, I'm going to change some of these scales just because I don't like to see that many dots on my graphs. Okay, so here's what this thing looks like, and the first question wants to know, is the function increasing or decreasing? So the function is always increasing. Alright, what does that mean in the context of the application? That means the percentage of Americans with diabetes is increasing. Alright, then part 2 says, what does this model predict the percent of U.S. adults with diabetes will be in 2022? So take our model that we have, we've got it in there. Alright, so just press trace. 2022 is 22 for this because X is the year after 2000. Hit enter, and then there's the number, around 23.66%. Alright, and then use the graph to estimate the year in which the model predicts the percentage will reach 33%. So in this case, this would be one of those situations where we could just do 33, graph it, alright, and then find this intersection. So come down to intersect. First curve, second curve, and then for the guess, it looks like it's touching way over here to the right. So just drag your cursor over there, or it looks like they cross, hit enter, and it looks like at 48 it hits 33, so 48.39. So in 2048 the percent will reach 33. Alright, so here's some basic properties of logarithms. This is the one we talked about earlier. Log base b of b for any b that's not equal to 1, that's positive, is equal to 1. Okay, we saw that way back here on part C. Log base 5 of 5 equals 1 when we transformed that. Okay, that's because any number to the first power is itself. Alright, that's what we're saying right here. Alright, log base b of 1 equals 0. Log base b of b to the x is just x. B to the log base b of x is x. Alright, and if two numbers are equal or two expressions are equal, then the log base b of those two expressions are equal. Okay, meaning that if two things are equal, then if we put them inside a log, we're going to get the same thing out of the log. Right? That should make sense. If we're putting the same thing in both logs, we're going to get the same thing out. Alright, so let's use the properties and see how we do on this. Log base 5 of 5 to the 10th. Alright, which property is that using? That's using this one. Log base 5 to a power, so that means we just get the power back. Alright, so by property 3, this is A, by property 3, log base 5 of 5 to the 10th equals 10. Okay, B, log base 4 of 4, that goes back to what we just said. 4 and 4, they're the same, so we get 1 out. So by property 1, log base 4 of 4 equals 1. Alright, by property 2, the log base 4 of 1 is equal to 0. Alright, and notice all these things work with the transformation we did before. 5 to the 10th equals 5 to the 10th. 4 to the first equals 4. 4 to the 0 equals 1. Alright, so you can also use those transformations to come up with these. Alright, D, log base 10 of 7. Oops. The log of 10 to the 7th. What I wanted to say is that's equal to, this is what we call the common log. If there's not a number down there, it's understood to be 10. Okay, if we don't write a number down here, it's understood that that number is 10. So this goes back to property 3, and we get 7. Alright, and then E, the natural log of e to the third, that's the same thing as the log base e of e to the third. Alright, and again by property 3, that would just be 3. Alright, e to the third, 5, 5, 10. Okay, these things wipe each other out, we just get the power. Alright, and then F, the log, this is the common log again, of 1 over 10 to the third. That's the same thing as the log of 10 to the negative third. Right, and just like before, if there's nothing written down there, it's understood to be 10. So once again, we've got property 3, and this ends up being negative 3. Property 3 is a very, very useful property because it drops that exponent down. Alright, now these other properties I'm going to do in a different video because these are a little bit more complicated, more complex than these first properties.